I'll try to stick to
No.
this phone here. Hi, everyone. My name is Shaowei Lin. I'm the Director of Research at Topos Institute. So before I give my talk, I thought maybe I'll say something about myself. My training is not in category theory. I was trained as an algebraic geometer, in fact, and in statistical learning theory. I work on this, for my PhD, I worked on this field of statistics called singular learning theory. I became very interested in spiking neural networks early in my career, and then later on moved on to program synthesis before becoming very enthralled with categories, and then decided to join the Topos Institute and have been thinking a lot about categories and type theory since. So today, my talk is going to be about AI-assisted coding, and this is a joint work between Topos and another nonprofit, Atlas Computing. So in this project, we are designing a roadmap for AI-assisted coding. I'm going to talk more about details of that roadmap today, yeah, I intend for this talk to be short and that we have time for discussions, because I think this is a topic that is kind of raising a lot of discussions these days out there. So what is the challenge we're trying to solve? First, we've seen how LLMs and ChatGPT in particular has allowed us to have more capabilities in terms of language translation and also searching for information. And in fact, like people could use these these language models to do things which could be harmful, like for instance, looking up how to create bombs or how to attack, say, very secure cyber physical systems. And in fact, there was a report that came out in February this year that Microsoft and OpenAI they discovered that there were hackers that were using ChatGPT to look up information on how to do cyber attacks, and they could even isolate about 5 or 6 different groups from different countries like China and I think Ukraine, if I'm not wrong, and other places. And they decided that, and they went to shut down these accounts to stop any further use of ChatGPT for these kinds of activities. But I think ChatGPT is just one of the many language models that are out there, and you can imagine that these kinds of attacks on our social technical systems is going to get more sophisticated in the future. So those are the intentional kinds of attacks, and you can imagine that as we use AI to develop more software and to make more decisions, there could be accidental mistakes that are made by these kinds of systems. So the question on in many people's minds is, how do we stop attacks like that? How do we prevent mistakes like that? And does it matter if these attacks are led by humans or led by AI agents? Some people who are working with existential AI risk would be worried that these kinds of attacks would be led by AI systems. So those are the kinds of questions that we're thinking about, and how we could improve the safety and security of these social technical systems. Now, we also know that we could harden these systems with formal verification. So you could come up with a mathematical proof that your system does not have the vulnerabilities that we are worried about. And the question is, if we could afford to not harden systems with formal verification, can we perhaps fix our social technical system by not formally verifying them, but by fixing them one bug at a time? So here's a really good example of a bug that was found in OpenSSL. OpenSSL is a protocol for secure communication over HTTP, and this bug is called the heartbleed bug. And in fact, the bug is very simple. Like in part of the protocol, you could be asking the server, "Are you still there? If you are there, reply hat." And then you're supposed to specify how many letters you want in the response. And typically you would say, okay, you need to respond with 3 letters because hat has 3 letters. But someone found out that you could actually change that number of letters to anything that you want. And it turns out the server is still going to reply. OpenSSL is still going to reply. And in the process, it's going to reply with all the other pieces of information that's appended in its memory. And from there, you could uncover things like passwords or what requests other people want and so on. So this was a bug that was very severe, and it was fixed very quickly. Okay, but still, do we want to be surprised by bugs like this, or do we want to design social technical systems that are provably safe? And just to show you how powerful these formally verified systems are, so this is a quote about the ComCert project. The ComCert project is about formally verifying a C compiler. I'm sorry, and in early 2011, when the ComCert project was still very young, okay, they took the underdeveloped version of ComCert and they tested it with many different kinds of basically data tests, and they found and it was the one compiler which in their project CSmith they could not find any wrong code errors. And this is not for lack of trying, because they have devoted about 6 CPU years to the task. So basically you can imagine the compiler being attacked with 6 CPU years worth of computation, and in the 6 CPU years they could not find any single bug. Yeah. So this and of course now ComCert is complete, and the new version of ComCert is probably even more secure than the one that it had in early 2011. And the diagram that I have below is a picture of the different languages, sub-languages that was involved in the compilation from C source, which you see all the way in the right, to assembly language all the way in the left. And the verification involved many different kinds of proof techniques and proof languages, and it was a big project involving many researchers. Now, this project is also an example of why formal verification is so difficult to do and why nobody does this, right? If you really need many researchers to verify something like a C compiler, what hope is there for the rest of us normal human beings, right? Not only do you have to write proofs, you also have to write specifications that make sense mathematically. Most people don't know how to write mathematically rigorous specifications, how you could write down implementations for those specifications, and then how you could connect the two by writing a proof. So it sounds like there is no hope in trying to formally verify our social technical systems. But we think that now with AI becoming more advanced, there could be a way to scale formal verification with AI assistance. And here in this little clip here, you see an example of the GitHub Copilot, where the programmer is writing in green a comment about what they want the code to be doing, and the Copilot generates a piece of code that actually does the right thing, right? And more programmers are using Copilot these days to do programming. And the question is if we could get this kind of AI technology to produce code, and not just produce code that works, but code that's actually correct. So, this roadmap exercise between Topos and Atlas is to looks at how we could go about achieving this in the near term. How do we go about scaling formal verification with AI assistance? And I will not have time to go into the full details of the roadmap, but I wanted to give you a sense of some of the important projects that we have in this roadmap, and maybe just an overview. So in this overview, we first talk about what is the workflow for verifying a piece of software. And here you can see that at the beginning, we start with the context of the problem that we're trying to solve. The context involves things like the logical framework that you want to use, the kinds of domain-specific language or specification language that you are using to talk about your application. And then there could also be legacy code and documentation for existing implementations of that software system. And then you go into this stage where you want to generate the specification. What is it that you're trying to prove? Next, you will want to generate implementations for that specification. And then lastly, you would, in addition to generating implementation, we are also generating a proof that the implementation satisfies the specification. And the last step is that we send the proof through a proof checker, something like a COG or Lean, and we have the machine verify in a very reliable way, mathematically correct way, that the proof is correct. Okay? And lastly, you will deploy that implementation in a system. And what's really important is that throughout this entire process that you see, there's back and forth interaction with users, human users. not just in designing the context and the final system that's deployed, but also interacting with the system on whether the specification that was generated, is it something that we want, or the implementation that we have, is it something that's efficient, and if the proof that was that was checked, is it correct, is it wrong, do we need to revisit the proof, and so on. Okay. Are there any questions at this point? Okay. So that's the broad overview of the workflow that we're looking at in our roadmap. And to kind of fill the gaps in the different steps of this workflow, we have many different projects. So we have projects that are related to the interfaces that are required between, say, for instance, the humans and the AI, and interfaces between different kinds of logical frameworks. We have projects related to context. We have projects related to generating specifications. And then we have projects related to generating the implementations. Okay, and I'm going to talk about some of these over the rest of this talk. Yes. Yes. Yeah, I will talk a little bit about that. Yeah, that's a good question. Each box here is hopefully a concrete project that can be done in 1 or 2 years, and with appropriate amount of funding and personnel. And we put this out there, and we say we put this out there as an invitation for anyone in the rest of the world who want to contribute to this larger goal of scaling formal verification. Yes, we are going to open up this roadmap, and then we are going to, of course, encourage everyone to develop open source software for this. Otherwise, there's no way we could put all this together in the final solution. Yeah. Yeah. I can also talk more about that later. So for Topos, we are very big on open source. Everything that we do is open source, open publications. We haven't thought that much as yet. I mean, like, are we going to use, say, MIT license or things like that? I think that would be our default, but we not actually decided on some of these questions. Okay, we also have dependencies between the different projects. This is intentionally a diagram that was made to not give the details of all the project names, but you can see that the projects are very intertwined with each other. So for instance, like the specifications which are generated by one of the earlier workflows could be fed into a later workflow where they synthesize an implementation from the specification. Okay, so I think we get to the interesting part. I'm gonna go into details about some of the projects, the more interesting ones. And so one of the first things that we really had to think about was the context and interfaces involved in a project like this. First of all, I want to talk about legacy code and documentation. So I think when people think about legacy code, they think that, okay, we have our traditional infrastructure like power stations, and they have code written for them, and they are usually written in Fortran, and it's very hard to change them. And if we want to secure our cyber physical systems like power stations, then we need to verify this legacy code and we need to fix its bugs. But I think that's a very narrow view of how legacy code and documentation plays a role in this roadmap. When we have now AI models in the mix, AI systems in the mix, this legacy code and documentation is very, very valuable information that could be fed into the AI system. And if you look at the projects for AI assisted coding out there, they almost never talk about this. They start from a clean slate, like, okay, give me a function that can generate give me a function that can generate factorials or test if a number is even. They almost always start from a natural language prompt, and then they forget that other software has been written. So in this roadmap, we are very aware all the time that we need to include legacy code and documentation as part of the process, that they should be fed into the AI system as either training data or as prompts or as documents that you could do retrieval augmented generation on, RAG. Okay, so please keep that in mind as we do the other step, look through the other projects. And then we also have to think about the many different specification languages. Here, languages is said with a plural, with an S. We are not designing only one specification language for the entire project, but we acknowledge that there could be many different kinds of specification languages that we need to secure for different kinds of social technical systems. And we need to work in that kind of a diverse, heterogeneous environment. Yeah, and another big part of the project is providing tools for translation between logics. So a really good example is translation from, say, something like Coq, which is a proof assistant, but also a programming language, to Lean. And Coq and Lean are very similar in terms of their underlying logic, but in terms of their programming language, they are very different. And in fact, most of the software verification stuff out there is written in Coq. It would be great if we could actually translate that over to Lean easily. But so far, there's no universal conversion from Coq to Lean. I mean, it would be something nice to have, but it's not out there yet. On the screen, you see an example of ChatGPT 4 and how it can already do translation from Coq to Lean without any. So basically, this is an experiment I did. I said translate the following from the Coq language to Lean, and here's a Coq, a piece of Coq code, and ChatGPT did not struggle at all. It was able to give me this Lean implementation, and in fact, what was surprising was that it did not just give me, for instance, this piece of code, instruction denote below, but it also gave me definitions for other things that it actually uses in instruction denote below. So it was very thorough in its solution. So that really quite surprised me, even though I've worked with language models before. Yeah, and you're going to see. So the question is how we could leverage language models in this way to build more quickly build translations between logics. And in fact, at the end of the day, we could send some of the translations through the actual parser and through the actual proof checkers to verify if they're correct. So this could be a very quick and easy way to build new translation modules. And then lastly, for context interactions, I want to talk about the interhuman AI module, which is actually one of the most important projects in this roadmap. Here, we're looking at interactions between three different pieces. The first is the proof assistant, the second is the AI assistant, and the third are human users. Okay, and even just thinking about the proof assistant itself, there are already a lot of moving parts. So you have, for instance, the logical framework, you have the specification language, you have the specification, the implementation, and the proofs itself. And even the proof is split up into different kinds of objects, right? You have the state of the proof, you have the proof script, and then you have the proof term itself. So the question is how all these different objects that you see on the screen are going to interact with human users and also interact with any AI systems which are assisting the humans in doing this formal verification work. And I think the theme, the kind of principle that we are using in designing our interhuman AI component is the principle that we've been talking about the last 2 days in our discussions, which is to look at formal, interoperable, and conceptual kinds of modeling. So here you can think of the diagram in the middle that represents the state of the proof assistant. That is the model that we have users looking at. That's the model that we have AI systems looking at. And formal would mean that this model that we see here has to pass a proof checker. It has to be formal enough that a proof checker could look at it and say this is correct or this is wrong. Conceptual means that it should be presented in a way that human users can understand. And that isn't necessarily in the same form that the proof checker is looking at. So a proof checker could be looking at, say, Galena. Galena is what Coq uses under the hood for representing its proof terms. But users, if they look at Galena, I think they're going to tear their eyes out. So you have to present it in a way that's more conceptual, that uses ideas that relate closer to how humans think about things. That could be like proof scripts, things like that, tactics. And lastly, it has to be interoperable. So you could imagine many different kinds of domains using different specification languages, and they have to talk to each other. And they have to not just have different domains talk to each other, but they also have, within a domain, we could also have different versions of the code, different versions of the specification. We should allow for natural evolution of the specification over time. That's how humans do specifications, right? We don't just decide, okay, this is what the power station is going to, specification of the power station is going to work at on day one, and then never expect to change the specification forever, right? The specification is going to change, and we have to understand that as part of the work process. And so that's part of interoperability as well. Okay. Yeah, so that's about the interface, and I can talk more after the talk about that if anyone's interested. So now I want to talk about specifications. How do we perhaps use AI models to help us write specifications? Okay. So I want to show a little demo. So I did this on GPT-4. I think the reason is that most of us have heard about GPT in the news, but very few of us have actually done some experiments to show how good they are at doing these things. So here's an example where I get GPT-4 to write down the factorial function and prove that the factorial function always produces positive integers. Okay? And bear in mind that I'm going to give it a request in natural language. And what you're going to see on the screen is that the proof assistant, sorry, the language model is able to convert that natural language request from me into a formal specification of what a factorial function is and what it means for it to be positive. Okay, so in Lean, write a factorial function and prove that it's always strictly positive. All right, so it starts explaining a bunch of things that's not necessarily important to us, but it's important for people who don't understand programming very well. So that's kind of nice. It defines the factorial function. Okay, great. That's good. It knows what factorial means. And then it says factorial of n is greater than 0. And then in the proof, it actually correctly applies induction, and then it shows the base case that factorial of 0, which is 1, is always positive, and then the induction case that it's always positive. Okay. So, fun fact, that program is actually wrong. I ran it through Lean. It's actually wrong. But the only reason why it's wrong was that here, if you see, whoops, that was a bit too far. If you look at the top, it says apply natural induction. This is a Lean 3 tactic. It's tactic for Lean 3. So in Lean 4, this actually breaks, which means GPT-4 was trained on data where Lean 3 was still the dominant version of Lean. And now almost everyone's using Lean 4. It goes to show that if you're going to use AI tools for formal verification, you have to worry about things like versioning, right? How are you going to deal with issues like that? These are the real engineering challenges. Okay, so quite impressive. What can we do? So why is generating formal verifications with a language model difficult? The thing is that you have a language model that's just producing tokens in a probabilistic way. Oh, yes, Brendan? I didn't try, but I would imagine that's correct. It should be correct because, yeah. So it's a very small mistake. I dramatized the fact that it was wrong, but it's just wrong in a very small way. Yeah. Okay. Yeah. So why is it difficult to get language models to generate formal specifications? So fundamentally, a formal specification is written in a formal grammar. LLMs aren't designed to give outputs in formal grammars. You can show that, well, in the example I showed, it was able to come out with Lean code that actually would pass the parser test. But if you try getting the language model to generate a piece of formal text that is 3 or 4, more than 5 levels deep, there have been experiments to show that language models are not good at hierarchical nested formal structures. Okay, and so the question is, what are we going to do when that fails? Are we going to just tell the language model, sorry, you failed, try again, and then we keep playing the replay button until it generates something that's actually correct? That's not going to work. So we need some more extra tools, strategies for getting language models to output formal specifications. And this is one of the challenges. It's an unsolved problem. It's an open problem. So if anyone has ideas on how to do this, that would be great. And yeah, the other question is, how can we use legacy data to generate accurate specs? You could generate specs from the code, legacy code. You can generate specifications from the documentation, which is probably even more successful way of doing generating specifications. But ultimately, I want to use everything that I have. I want to throw code, documentations, everything into the language model and hope it comes up with some kind of a good specification that summarizes what was done in the code. So this is also one of the projects in the roadmap. Okay, and then so now I come to the last part of the roadmap, which is about synthesizing implementations. So assume now we have a specification that was generated in the previous step. How do we synthesize a piece of code that meets those requirements? And first, we have to understand that there are two kinds of logics that are used often in formal verification these days. The first kind would be what I call decidable first-order theories. So these kinds of theories involve some kind of Hoare logic or separation logic, and they are used in verification-aware languages like Daphne or Pharmacy or Virus. Virus is for Rust. And in these languages, you could give an implementation, and the proof assistant, the programming language, the programming IDE is actually able to check if that implementation fulfills the specification in a decidable way. There's an algorithm that terminates, and it will terminate with either a proof, or it could tell you your implementation doesn't satisfy the specification, and here's a counting example. Okay, and I just want to show you an example of GPT trying to generate something in a decidable first-order theory. Right. So in this example, we're telling GPT that you're an expert in Daphne, which is a C-like programming language. Find the conditions for finding the maximum element of an array. Okay, and then you have to provide some kind of constraints, like do not assume that integers are always non-negative unless necessary, and so on and so forth. And then what you want GPT to do, you write a to fill piece of text, and then GPT will fill in the text with preconditions and postconditions. All right, so we tell it to find the maximum of an array, max array, and it sees that it fills in it requires that you have an element, that you have a non-empty list, and then the output, which is the ensures that you see up there, ensures that it truly is a maximum element and ensures that this element exists in the list. And it's also able to construct what we call loop invariants. So those are invariants as you run over the loop of checking everything in the list. Okay, so GPT-4 has no problem programming in Daphne or Pharmacy, and so this is one of the ways we could use GPT-4 to generate programs, synthesize programs. Now, the ones which I think is more difficult is with what we call expressive higher order theories. So I'm thinking mostly about dependent type theories, and they are the kind of theories that we see in proof assistants like Coq and Lean. Okay, and here you see that here's the example that was generated earlier, where we had GPT-4 generate a proof that a factorial is always positive. And the language here is higher order because it allows you, it has dependent types. It allows you to work with this natural induction, which is a theorem that operates over predicates, and you cannot do that in Daphne or pharmacy. Okay, and when you work with expressive higher order logics, you no longer have decidability in terms of checking if the implementation fulfills the specification. You really need humans to come in and provide some hints or strategies or tactics to aid the proof process. So in trying to solve this problem of synthesizing programs in expressive higher order theories, one of the most successful methods out there is called refinement-based synthesis. Okay, here, the way that the program is generated is by using something called refinement types. So at the top, you see an example of trying to synthesize a program, a function that can insert a new key value pair into a cache that we call L. So if this cache still has space, you just pop it in. If the cache is full, you might have to kick out some other key value pair in order to put in this new key value pair into the cache. All right. And so one of the basic specifications we could have at the start is that we want a new cache state L prime that perhaps is a subset of the new key value pair appended to the old cache, and that you only require it to be a subset. So there's no other requirement there. But through the process of refinement, you could add more implementation details. For instance, if the key is in the old cache, then do this. If the key is not in the cache, do this. If the key is in the cache, then do this, and so on and so forth. So we refine the goal to a state, until it becomes something that could be read off completely as an implementation. So this is refinement-based synthesis. And the theory behind this is actually fascinating. They use something called the non-determinism monad. They also use chi-State categories and power sets. Aside from the mathematical theory, this is truly a synthesis method that not only gives us correctness or functionality, but also gives us algorithms that are performant or effective, efficient, that runs fast. So for instance, one of the success stories out of this kind of synthesis method is the Fiat Crypto Library by MIT, Adam Chipala's group. And it's estimated that today, more than 95% of HTTPS connections by browsers actually run the generated algorithm by his lab, right? And it's fast, that's why people use it, and it's correct. And it solves problems that you could face maybe, if you think back to the OpenSSL bug that I was talking about earlier, this is a big deal for people. We really want verified cryptographic libraries for our internet traffic. So if we go into detail about how this refinement-based synthesis happens, in fact, refinement-based synthesis is an example of correct by construction synthesis. It means that number one, you construct your program or your proof by a series of tactics. So the tactics actually tell you how to transform the proof state. Secondly, what you have at the end of the day is not just an implementation, but something that we call a code carrying or implementation carrying proof. The implementation and proof are kind of fused together. So you actually need one more final step where you extract the implementation from the proof. So in correct by construction synthesis, the proof and the implementation are generated together. Then you have a very strong guarantee that the implementation that you have is actually correct because it carries a proof with it. And so here's an example of the kinds of tactics that were used to generate the insert key function that I had over here. Okay. And then so here's the point, right? We are used to seeing. Here's the point of my entire talk, which is why we should do correct by construction, not by generation. We are used to seeing language models generate programs token by token, line by line. You saw videos of the language models doing that. That is not the future of AI-assisted coding. We should tell people to stop believing that that is going to solve our programming issues. Well, GitHub Copilot does that. So maybe that's okay if you have small programming problems. But if you have larger, complex software projects, I don't think token by token generation is going to solve your problem. You want to have solutions which are correct by construction. Okay? And in fact, that's how humans construct problems. We construct programs. We construct them by decomposing the goals. We compose the solutions in sometimes non-trivial ways. And then after we have a solution, we might even modify or refine the programs over time to get better programs. Okay? And so if we want to get AI systems that can construct programs in this way, we need AI systems that actually learn how to use tactics, and not just tactics. It has to be generic tactics. Okay, so if you look at this list of tactics that I show you over here, how many of these tactics were just relevant to finding, relevant to programs that regarding cache and their operations, right? Look at this: refine, replace, use key, add tactic. How many times is this tactic going to be reused for another problem? Okay, how do we, if this tactic is not going to be reused for another problem, how do we expect the AI model to actually learn to use tactics that can be applied across many different problems, right? We have these AI models that are supposed to be good at generalizing, and if our tactics do not generalize, then we cannot expect the AI models to learn how to use them. So we need to define generic tactics, but how do we define generic tactics? And the answer is category theory, because category theory is about finding generalizations across many different similar structures. And this is the reason why I joined the Topos Institute, because I wanted to understand how category theory can help us design generic tactics. And in fact, we are not just developing tactics for categories. More precisely, we're looking at algebraic theories, generalized algebraic theories, okay? And we want to implement these generalized algebraic theories as type classes in Cog or in Lean. And a very good success story of type classes is this project called Mathematical Components. How many of you know about this project? Okay, Peter, all right. In fact, if you've heard about the four-color theorem, the computer proof of the four-color theorem, the latest attempt that was done in Cog, okay, and there was also the proof of the Kepler theorem, if I'm not wrong, in Cog. I could be wrong about that, but both of these, sorry, not the Kepler theorem, but the Hales-Hewitt theorem from group theory. Both of these theorems were very difficult to prove, and the only reason they could do this in Cog, that Gontier and his team was able to do in Cog, was that he used type classes to generalize tactics across many different mathematical structures, and he built automation around these type classes. It's a beautiful piece of math, beautiful piece of work. And what I really hope is that we could take the insights from that mathematical project of building and proving very difficult math theorems and use those insights to build complex software systems. Take type classes that we have in mathematical components and ask, what does it look like for software systems, to build type classes for software systems? What does it look like to build tactics for software systems that generalize well across many different software problems? Okay, and I think here are some other projects that we have in synthesis. I will skip this and we can talk about this if you have questions. And so here's the summary. Okay, the challenge was to scale formal verification with AI assistance. We need many different steps to do this. First, we need context. We need to feed the AI models with legacy documentation and code. We need interfaces which are formal, interoperable, conceptual. We need specifications because ultimately humans are the ones which are going to give the specification in natural language, and we need help from AI systems to convert them into formal structures. And lastly, we need synthesis of code, and we need to do it by construction, not by generation. Thank you.
Objections, protestations.
Can you say a little bit about the proof repair? I'm interested in that because sometimes it doesn't work. And how do you envision that AI will help problems that come on the first round?
So proof repair is a concept that Talia Ringer came up with in her thesis, and she's done quite a bit of work on that. And I really like her work. So she talks about something called proof engineering. Proof engineering is like software engineering, but with proofs. And so she envisions that in the future, most of the work will be around proof engineering rather than software engineering. And proof repair is a critical part of this, where you could have, say, a specification that changes, or for instance, we update the specification to include some vulnerability that we didn't know before, or we update the libraries that we're dependent on, or we update maybe a certain way that we want to make something more efficient, and we update the implementation. And then proof repair is supposed to automate the repair of the old proof so that it now fulfills the new proof. And there are kind of two ways that I've seen this happen. The first way is you could use the AI assistant by where you feed in both the old specification, the new specification, the existing proof, and then the proof error. And then over time and training, the AI system becomes good at telling you what changes you should make to the proof to make it work. And it seems that this work by Ringer has been quite successful with small problems. Another solution that she has is doing transport. Something like she talks about univalent transport in her thesis. So the idea is that if you change the way you represent a type in the specification language, but the new type is actually equivalent to old type. The question is how you could transport old proofs over to the new proofs, and it's quite interesting that you could do it in a way that's similar to how univalent transport happens in homotopy type theory. Yes. So if you look at ComCert, I think they actually the key. I think I'm probably wrong, but one of the key specifications they're trying to prove is basically a bisimulation claim, and most of the projects in these verification projects for these decidable first order theories involves proving specifications that talk about bisimulations. Yeah, Ringer, Talia Ringer.
Okay, so I have a simple and practical question. So right now, software engineering, before large language models has been done by humans, and you refer to humans that humans do not generate code by next token, but they deconstruct their concepts and logic. So now with large language models, as you pointed out, it can do some simple things, not always correct. So then humans generate this unit test that's much simpler than proofs, right? It's just for certain inputs. And then things change and units tests are used or they change themselves. So there is a lot of change. So my question is, it seems like the concept here is that instead of teaching or using a human, we would have a different AI agent that does it more like a human and not like a current large language model that just generates next token. So, and in that case, if you succeed, then you would basically have a replacement for software engineering because it would be doing the same functions. And you said that it might be proof engineering that humans will sort of get into instead. So I have a more, I guess, a practical and maybe even philosophical question is, as flawed as it is now, it's not capable of replacing a human. We're not talking about really some kind of superhuman intelligence at all. We're just talking about some assistance, and humans are not only in the loop, but they're actually superior. And as you said, if you have something complex, these large language models would not be able to do most of this. But if what you are suggesting succeeds, then we're talking about a replacement. And that's what so many people are afraid of. And my question is, why would you have that goal at all? Why not to teach humans all these concepts? And as you said, there are some general concepts. So why not to focus on the humans and try to find a replacement in that model?
That's a very good question. I love that question. So actually, I'm advocating that we don't replace the humans. I don't believe in an AI that can do everything. I don't believe in AI personification. I believe that AI will help us in different parts of our workflow. So for instance, in this workflow that we have here, my hope is that we have small little AI tools that could help us in different various stages of this. In fact, maybe I'll show you a video of an example called the Lean Copilot that's assisting the human in improving something. But yeah, let me start with that first, and then I wanted to dive a little bit deeper into your question. And thank you for that question. I really like that question. So here's an example of the Lean Copilot. It is a project that is associated with another larger project called Lean Dojo, which is about integrating Lean, which is a programming proof assistant with language models. All right. I think it has already started without me. So here at the beginning, you see that this human is trying to prove that addition is commutative, right? A plus B plus C is equal to A plus C plus B. So it could ask AI model for help by saying, suggest some tactics for me. And then the list of suggestions come out on this side. And then you could then click on one of the tactics, and then the proof system will continue to run. And if the human gets stuck, the human could say, suggest another tactic. Or the human could say, suggest a proof, search for a proof, and then the AI system could maybe generate an entire multi-line proof. But often that doesn't work. In this video demo, they actually say that most of the time that doesn't work. And the last one is that you could, for instance, in this example here, actually search proof just does not return anything. And lastly, you could, for instance, ask the AI model to help you select premises or lemmas or theorems that you could be applying in your proof. Okay, so I also see the AI model as helping us in designing these specifications, right? And it may not show up in the case of the proof assistant. It could be a different component that the humans use in designing specifications. It could be a graphical interface where the humans can actually see the specifications in terms of the different objects or resources that it cares about and how they're connected, and how we have verification that you will never spend more money than you have in your bank account, for instance. And I imagine that as with most other technologies, the way that the AI assists the human will eventually disappear into the background, so much so that we almost never know that it's there. Rather than maybe a robot AI overlord that's standing next to us and like commanding us and telling us how to do everything. So I think that is the kind of goal that we're hoping to achieve in these kinds of systems is that number one, the human has the driver's seat always. We are always building systems that allow for this back and forth feedback from the human at every single step of the way. All right. And then somehow the AI assistant should just disappear into the system and become a very natural part of the background and not become a black box that solves everything. I hope that answers.
Thank you.
Question.
I have a comment and a question. The comment responding to your comment. First, thank you for making that point. I think it's really incredibly important, and so much so that I want to respond to it directly from an institutional perspective on behalf of Topos. Like, we're very concerned about the drive to replace humans in the construction of AI technologies at the moment, and we view a very deliberate part of our work as trying to provide a positive alternative, like a different sort of philosophy and sort of sociology of AI that will, still respond to the positive things people want to construct AI technologies for, but in a way that centers human agency and collective human agency, the ability of society to determine its future in a way that allows all of us to flourish and live according to our values, and certainly not in a way that replaces people, that causes a large amount of social disruption, that creates threats to society, or more inequality or anything like that. So it's interesting to me to hear you sort of still see, I guess, some shade of that sort of human replacement approach to AI in this presentation. And I would very much welcome much more discussion in terms of what you see and how we could improve. And I think everyone here, I know Shaowei would, and in fact anyone at Topos cares a lot about this. So thank you for raising that, and please, continue to raise it and to specifically engage with us on issues there. For Shaowei, sorry, Alexander, I'd love to hear your comment too. This is a bit of a transition, so we can coordinate over like how to have this discussion, especially given the time.
Yeah.
But I'm interested in what assumptions are implicit in your presentation about what generative AI will look like, say, over the next 5 years. And yeah, the technology is changing very fast, as it's led by these big AI companies. So you need to, in some sense, do some forecasting to construct a sensible roadmap, and your assumptions seem to have been implicit rather than explicit. So I'm interested in you explicitly surfacing this.
Yeah, that's a very good question. I don't think I've actually talked a lot about. In fact, I don't think in our roadmap we've even discussed explicitly what the assumptions are for AI models and how they're going to change. But I would say that I expect AI models to become better at retrieval. So, for instance, instead of explicitly training the language model on, say, Lean-4 code or things like that, you could say, okay, here's what the Lean-4 grammar structure looks like. Here are the changes from Lean-3 to Lean-4. All these are given in documents that the language model could access and refer to in doing translation, for instance. So I expect that document retrieval, document augmentation, generation that's augmented by documents will become better over time, and I hope that it does because otherwise we're going to spend a lot of money retraining language models. The second thing is that I expect that these models will become smaller and that we could maybe run them on our own laptops instead of like running on the large servers out there. Since we are asking them to do very restricted tasks. We're not telling them to translate German to English or anything like that. We're just telling them to do some kind of formal structure prediction. And the third thing is that I expect us to move away from language models. In fact, I hope that we create more reinforcement learning algorithms for this. This is a clear application of reinforcement learning. I mean, token by token generation is a very primitive way of doing reinforcement learning. I would just say that. Yeah, so to start.
Yeah, thank you very much for this inspiring talk. So can you go back to the slide on the workflow?
Yeah.
And then maybe I have another question if we have time for that later.
Sure. Or in the break, during the break.
Yeah, I was right at the
Yeah.
Yeah. So when I did my PhD in 2000, I was kind of in a software engineering kind of group, and so really at the time you needed a PhD to learn one formal method, and then you were like one of a dozen people who could apply that formal method to actual software engineering. Right. And so I very much share, I mean, the enthusiasm about this project, because finally, right, so maybe we can start fulfilling the promises we made at the time. But like what it seems to be like, maybe I'm misunderstanding the workflow, but maybe to me it looks like you take the old-fashioned workflow and you want to use AI and large language model to kind of augment it, to make it better. I think that could be a complementary approach to the whole problem, which is just to look at how software engineers are using AI and large language models right now in their practical day-to-day programming, and then look at these workflows and kind of ask the question the other way around, right? So how could we bring in formal methods to kind of improve what they are already doing, maybe without the aim to going for full-scale correctness by construction. Well, yeah.
Yeah, that's a very good question. I would love to hear your thoughts on how we could improve current existing workflows. One of the ways that I'm seeing some kind of more formal methods going into existing software engineering practices could be like, for instance, a shift from JavaScript to TypeScript, right? Or the shift from there's F-star. F-star is a language that's supposed to be very good, not just at proofs, but also at writing functional code. Lean is starting to move towards that. So you could write code, not have it. You could write parts of the code, verify parts of it, and then have other parts which are not verified, for instance. I think they are all good changes in the field, but I haven't really thought about how we could incorporate that into this roadmap, and maybe this is something I'll need to discuss more with.
So my colleague Jeff Turner, he just finished teaching a course exactly on that topic here at Chapman. So maybe you want to comment?
Yeah, sure. I mean, I guess my view is one of the challenges is the way that these LLM systems are currently architected. They're not compositional in nature. And so when you're training a not natively neuromorphic network by feeding it lots of data, you don't have the logical inference or the logic embedded into the system to reason about the output, that code that's being output. Therefore, what you need is to have some formal methods integrated into these systems. One of the things I've been examining this semester is how do we create more composable approaches with MOE, right? Because you could imagine there's a new...
Sorry, MLE?
MOE.
Oh, MOE.
A mixture of experts.
Oh, mixture of experts.
Yeah, so one of the systems that just came out, for example, is Arctic from Snowflake. It's got 128 experts built into it. But because the way that the bridging and routing functions work, there's basically just a bunch of feed through data to build these things up. If we can create hybrid approaches that don't use either the dense or necessarily the MOE approach, perhaps we can embed some of those formal methods into these things and use things like operational semantics plus better visualization tools so that we enhance the IDE experience as you're going through these workflows. So those are just my thoughts on the subject at the moment, and they change from week to week because there's so much stuff coming out that's so new.
Thank you for that. I definitely would love to get your contact after this and find out more from you. We definitely have been thinking about compositionality and language models a lot at Topos, and would love to hear.
Yeah, one of my colleagues likes to say that we've got MOE because we don't know how to compose ANNs. It's Forman's composition.
that we need here to thanks Shaowei for this inspiring presentation and go to the next one. Thank you very much.
Thank you.
Thank you very much.